Right, grade 12's matrix. Okay, we are revisiting again momentum and impulse. Now, last week, almost said last year, but last week we did introduce momentum and impulse, starting with the following formula, the simple momentum formula. P is equal to mv, of course, which is mass times velocity. Okay, introducing that the units of measurement is measured in kilograms per meters per second. We also introduced the change in momentum, all right, when the momentum shifts in another direction. And we did a few examples of those as well when we had a look at change momentum, PF, momentum final, sorry guys, minus momentum initial, which was m as the common factor, Vf minus Vi. That's essentially what it was. We also looked at Newton's law. In terms of momentum, I'm going to try and shorten it. Newton's second law in terms of ITO, momentum, in terms of P.
Are you writing something?
Oh, thanks, Will. Maybe reminding me, maybe my share screen is not working. Let me just check. Found that formula to be F net is equal to the change in momentum over the change in time. Okay. And I'm not sure if we were doing an example last week, but if I can give a short example, here is that I think we did this example maybe of the rocket that was launched from rest, and it reached 12 meters per second in 3 seconds. Okay, and the question would be to calculate the change in momentum of the rocket, and then also calculate the net force experienced by a rocket. Okay, well, the change in momentum is quite easy. We would use this formula over here. Okay, and if we had to calculate the net force, we'd plug it in over here. So that's pretty basic. Okay, let's see. Anything we need to uncover this week? No, we don't. However, let me just check. Well, what am I saying? Of course we need to cover something this week. We need to cover something that is called a new topic, which I'll start on a new slide. Impulse. Okay, we're going to start impulse this week. Now, the first question that we might ask ourselves is, what is impulse? Okay, what is this new term? Okay, it's funny that you all should ask. I'll give you the answer. Okay, impulse, as defined, okay, is the product. Okay, so there's multiplication involved of the net force or resultant force. All right. That is acting on an object. Let's just get all this in here. That is acting on an object, and the time the net force. Just make sure I'm not getting my words mixed up here. Okay, I got the product of the net force acting on an object and the time the net force acts on the object. So the time that it takes for the net force to act on the object, as well as the net force value. Right? So the net force value, the net force, all right, times the time it takes for the net force to act on the object. That's essentially what it means is in simpler terms. Okay, so in other words, we have the formula saying, let's get blue, impulse is equal to F net times delta t. That's essentially what it's equal to. That is impulse. But what does this also remind us of? If net times delta t also reminds us that that's what's equal to the change in momentum. Right? Remember, the change in F net is equal to the change in momentum over the change in time. Therefore, we rearrange this formula and we have our impulse formula, which is F net times delta t, which is also equal to the change in momentum. Right. It is a vector quantity. Okay. What is it measured in? Depending, all right, impulse, if we calculate just this part over here, newtons per second. Okay, but when it's equal to the change in momentum, our answer can also equal kilograms per meters per second. But most often than not, it's measured in newtons per second if we are using F net times delta t. All right. Now, how does that formula, or this part of the formula, come about? Okay, let me explain it. It is called the impulse momentum theorem. Okay, the impulse momentum theorem. Okay, now what that states is that I've got my Newton's law in terms of momentum. If net is equal to delta p over delta t. Right? We're happy with this formula. We've seen it before. If I rearrange this formula, which I showed you early on, I have F net times delta t gives me my change in momentum. Okay? It gives me my change in momentum. Okay, now my change in momentum can also be broken down further, is to saying that F net times delta t can also equal mass times the change in velocity. Remember, delta v is vf minus vi, essentially. Okay? Therefore, I can conclude that my impulse is also equal to my change in momentum. So they are equal to each other. Okay? And the best way that we're going to discover this is by having a look at an example. Okay? An example would be, let's take the example of a let's find a simpler example here quickly. Where they actually ask for impulse. Let's take a 500 gram rubber ball, or let's take a rubber ball in general. Okay, so we have a rubber ball, alright, just like this, and we have a little bit of a wall here. Okay, that's a rubber ball that hits a wall at a velocity of 20 meters per second. Okay, so we have 20 meters per second over here, and that's a rubber ball. Okay, one of those little bouncy rubber balls. Okay, I have a stress ball that I keep here when I get stressed out. It's quite fun, squeeze it, but it can also bounce off a wall pretty neatly. So I often just throw it against the wall, catch, throw, catch, throw, catch, throw, catch. My mom gets upset with me because it makes a lot of noise, but after a while, repetitively. But I'm gonna take a bouncy ball, stress ball, same thing. It bounces off a wall, and it makes contact with the wall for 0.1 seconds. Okay, so it makes contact. It's a very short time. I mean, and this is practical at the same time, because if you bounce the ball off a wall before, it doesn't make contact for very long. Okay, the momentum of the ball changes. Now they give us the change in momentum is 15 kilograms per meters per second. They say that the momentum changes by 15 kilograms per meters per second. Ignore the effects of gravity and air resistance. Take the initial velocity as positive. Okay. Now, the first question is, the magnitude and direction of the impulse that the wall exists on the wall. So if they ask you a question here, they ask for impulse of wall on ball. Right, that's what they're asking for. That's the question. Okay, now what is simpler to denote is that we've got a change in momentum, but we also know the impulse formula. Okay, we know that impulse is equal to F net times delta t is equal to also my change in momentum. So impulse equals change in momentum. That's what it means. Impulse formula, F net times delta t. Okay, impulse momentum theorem is that my impulse is going to equal my change in momentum. So they said that the momentum changes by 15 kilograms per meters per second, meaning that the ball bounces obviously off the wall that way. Okay, it's only here for 0.1 seconds. So my impulse is going to equal negative 15, all right, newtons per second, because this is essentially what it's equal to. Therefore, my impulse, which is this bad boy over here, is going to equal 15 newtons per second, which is going away from the wall. Alright, and that's essentially what is happening in this scenario. Okay, now where does the impulse formula come a bit into play is when they're asking you to calculate things such as the net force or calculate things such as the time based on the change in momentum, etc., etc. So for example, if I asked you to calculate the net force, all right, I want the net force now of the ball. Okay, the net force of the ball. So what am I going to do? Well, I'm going to say, well, impulse is equal to my change in momentum, which I found out to be negative 15 or 15 newtons per second away from the wall. And it made contact for how long? 0.1 seconds. If net times 0.1 is equal to negative 15. If net is therefore equal to negative 15 divided by 0.1, and therefore F net is equal to 150 newtons away from the wall. It's first negative 150, but I just went straight to the last step, away from the wall. Now, let's take a graph, for example. Now, what happens if in a question we get given a graph? Okay, like this. And on the left-hand side of the graph, we have net force. Right, we have net force, and net force we know is measured in newtons. And here we have time, delta t. And let's say the graph goes something like this. And like that. Okay, so we obviously have presence of a triangle. Okay, like equations of motion, which I'm sure we might have covered last year, is that there's certain areas underneath certain graphs that can help us work out another variable with an equation of motion. If not, we'll definitely learn that this year in equation of motion. Alright, but no, it was visited in grade 10. So we have net force versus time, which we know is the impulse formula. Alright, F net times delta t. Alright, that's our impulse formula. But now, what happens if we get given a graph in our question? Alright, we know that this is clearly a triangle, so we know what is the area of a triangle. Alright, the area of a triangle is equal to half base times height. And we clearly have some area underneath here. We can drop a dotted perpendicular here, and we could have two right angle triangles, so to speak. Alright, an imaginary line in the middle. So if I have a look at an area under the graph, alright, let's write that down over here. I've got the area under the graph, which is this section here. This is the graph here, this is underneath. Area under the graph, we know is going to be equal to this formula, which is half base times our height. Okay, basically half base times height is basically taking average force multiplied by time. That's essentially what half base times force is, right? Half base times height. Okay, and if we do that, basically it's the same as saying F net delta t, right, which is essentially is equaling impulse. What am I trying to say is, if we're given a graph of net force versus time, all we need to do is find the area underneath that graph, no matter if it's in the square shape, rectangular shape, no matter what shape we get that we can perform an area formula. The area underneath a force versus time graph will equal impulse. Okay, nice little hack there for you guys. Just a note, guys, when I say drop a perpendicular, I just have to drop a fairly straight-ish line. Obviously you guys would do this with your ruler over here, and then obviously whatever units here will be my base of this triangle, and whatever units there would be the base of that triangle, and obviously I'd have, with this case, be half base times height in brackets multiplied by or not multiplied, sorry, if it was equal it would be times 2, but since it's not equal, so plus another half base times height, and that will give us the value of our impulse for this particular object. So what I want to do now is just give you learners and you students some practical examples of impulse, of the impulse momentum theory in everyday life. A place called or a zone called crumple zones, alright, which are in like the front and back of modern cars during collisions. Alright, I was involved in an accident last week Friday. Car isn't damaged excessively or majorly, it's just a broken headlight, but for example I still collided with a back of another car. Okay, so the time delta t it takes for the car to crumple in the result of a collision is the time it takes for the car to come to a rest. Because remember, if the car stopped at a decent distance away from the car that was in front of it, it wouldn't have needed a crumple zone, or wouldn't have needed the car in front of it to bring it to a stop. Right? Make sense? So the crumple zones during collision, the time it takes for the car to crumple is the time it takes for the car to come to rest, and also change the momentum. In other words, from a large value of momentum, because the mass of the car times the velocity it was going, and bring it down to 0. Kind of like our previous question in that practice exercise when the car was brought to a standstill. Okay, which is what cars are normally brought to a standstill at traffic lights, unless you're a taxi. Not that often. Now F net, which is the force to stop the car, is smaller due to the longer impact time, which reduces the chances of serious injury. Okay, the force that the car exerted on me when I was in my little collision was quite small, because I still managed to stop at a fairly good distance apart. So the time that it took for me to crumple was quite short, and I wasn't injured at all in the collision. That's another example. That's one example. Another example could attribute to a cricket player who moves his hands backwards as he catches a ball. Right? If any of us have played cricket before, and we've been under the high balls, obviously the batsmen are aiming for a 6, and we, the fielders, our hands go up, and as the ball comes towards us, we lower and lower our hands so the ball falls safely into our hands. Now that's just practically what happens on a cricket pitch. But the science behind it is that this increases the time taken to stop the ball, and so the net force on the cricket player's hands is smaller, because that ball is coming down at a very strong force, at a very strong, very well, I wouldn't say very strong, but I mean fairly strong gravitational force. Cricket ball's very hard, and that ball that was hit at a certain force up in the air is definitely coming down, in theory, if not at about the same force that it was hit. Alright, mass times gravity as well, given to the gravitational force as well. So the cricket player lifts his hands up, and as the ball comes towards him, he lowers his hands so that the force is a bit smaller, because the time therefore increases that it takes for the ball to get to his hands. It obviously increases, and the F net decreases. That's a perfect example of the impulse momentum theorem in real life, for those of us that love cricket. Did that make sense to everybody? And grade 12s, that wraps up our lesson today on impulse. Pretty straightforward. And next week we move on to the conservation of momentum, so stay tuned for the next video.